Okay, good afternoon, everyone. Today is going to be the review day, so before we start, really quickly, Daria, what time is your Wednesday session?
It's 7 to 9.
7 to 9.
Yes,
and it's a different room.
Yes, it's Jones 201. 201, yes.
Okay, so for studying for the exam, all right, there's going to be 2 more opportunities for office hours, basically. There's going to be, my office hours are going to be today from 4:30-ish to 6 o'clock-ish. Okay, I have an appointment today at 3:30. So I think I'm going to be home at around 4:30, but it might be a little closer to 5. I'm not sure, really. But I'll go for at least an hour and a half starting at that time. And if that time really just doesn't work for you because you have a time conflict, then just send me an email and I'll schedule some extra office hours tomorrow for you. SI session tomorrow from 7 to 9 in Jones 201. Okay, and homework 2.1 to 2.2 is due today at 11:59 p.m. So it's 11 questions long. If you want help with it, then just come to office hours today. And our exam is going to be the day after tomorrow. Eric, do you mind? Thank you. Yeah. Please make sure your mask is all the way over your mouth and nose. I posted a practice exam on Blackboard, and I also put the solution video onto YouTube. Just out of curiosity, has anybody tried the practice exam? Okay, out of the people who've tried it, can I get some, I don't know, some of your thoughts on it? What did you think? Let's start with Brendan.
I thought it gave me a fairly good estimate on what I should expect to get on the exam based on where I'm at currently.
Okay, so Brendan says it gave him a good idea of what he needs to practice for the exam and how he's going to do on the exam. Morgan, did you have some thoughts?
I agree.
Morgan agrees. Who else took the practice exam? Who has something else to say? Hannah?
It made me understand that the questions that I thought were going to be asked aren't going to be asked, and it's just a lot more vague than I thought. So
Okay, so the questions weren't exactly what Hannah was expecting. Okay, so that might be something that you want to try out. How about you, Hudson?
You have to know how to go forward and backward.
Sorry?
You have to know how to go forward and backward when applying things. Yeah.
Okay, you have to know how to go forward and backward. Okay, so all of this, I think, should give you an idea that the practice exam is really something that you should definitely look at and try, because the questions that I'm going to ask on the exam are, not going to be of the sort where I just say, here's an equation, solve it. It's most of the questions are going to be application driven, because this is an applications course, so business applications and those sorts of things where you're going to have to read word problems. Okay, so sometimes the word problem, it can be tricky to translate the word problem back into an equation and then do the equation stuff and then go back to what it means for the word problem. Okay, so that interpretation in both ways is going to be a big part of the exam. Okay, so those of you that did the practice exam, did you see the solution on YouTube?
I just saw the uploaded copy.
Okay, let me double check that the solution's on YouTube. I know I posted it, but sometimes it doesn't work. Let's go to my channel. Okay, practice exam 1 solution is on there. So take a look at that. I recommend that you try the practice exam on your own first. Then go look at the solution and see how your answers match up to the answers that I give in the solution guide. Yeah, Eric.
Can we take the practice exam?
Sorry?
Can we take the practice exam multiple times?
Oh yeah, sure. It's just on Blackboard. So it's just like a PDF. You can download it. You can print it out if you want, or you can work the solutions on another sheet of paper. Yeah, you can take the practice exam as many times as you want. But I do want to make sure that I communicate to you guys that the practice exam is definitely not going to be like a carbon copy of the actual exam, okay? What it's designed to do is give you a selection of some of the topics which are going to be covered for the exam, okay? The questions on the actual exam are not going to be the same as the questions on the practice exam, but the material should be more or less similar. All right. Any questions, administrative questions before we start the review? Yeah, Gino.
It's like the exam divider in certain articles are all like short answers.
There will be a true and false section. So the second page, usually I do a true and false, A through E. You put true if you think it's true. If you put false, you have to briefly explain why you said that is false. Yeah.
Is it out of the same number of points as the practice exam?
No, it'll be a different amount of points. It might be a little shorter than the practice exam. I haven't decided yet. Okay. Any other questions? All right, then let's start the review for today. So I think what I sent in an email was I'd like for students to bring questions to class that we can work on. If nobody has questions, I can find something for us to work on. But I'd like to start with what you guys think is maybe the muddiest point of what we've done so far, something that you were a little confused by, something that you want to see an extra example on. So does anybody have something lined up for me already? Brenda?
I was thinking about finding the instantaneous rate of change of a linear function.
Okay, sure. So the question was, how do we find the instantaneous rate of change of a linear function? Okay, so let me go back to the section on instantaneous rate of change. Okay, so I think this is the key section from the lecture, which says that, okay, the instantaneous rate of change of a function for a given input is just the slope of the function at that input, right? And the other word we had for that was it's the derivative of the function at that input, okay? So the way we write that is with f prime, okay? This means derivative. Now let me write that down. So this is derivative of f at a, or evaluated at a, okay? And that's also equal to the slope of the tangent line to the function at t equals a. So let's think about that for a second. If we were to have a linear function, so the question was, what's the instantaneous rate of change of a linear function? So let's say I have a linear function here. Okay, I guess it's going up, right? Well, the instantaneous rate of change, okay, at a given x value, t equals a, so I don't know, maybe here's a, is just going to be the slope of f at t equals a. So if we have y equals mx plus b, or why don't we say y equals f of x equals mx plus b, right? Then what is going to be f prime of a in this circumstance? Yeah, just m. Okay, so the instantaneous rate of change is just the slope of the function at that x value. Well, the funny thing about lines is their slope is constant, right? Their slope is constant. So it's just m, okay? In fact, we could even move a somewhere else, right? We could move our point A somewhere else. Well, the slope of the function here is m. The slope of the function here is also m. So whether we do a or whether we do b, we're going to get f prime of a equals m, and so does f prime of b. Okay, because a linear function has a constant rate of change. So if the rate of change is just the slope, then the instantaneous rate of change at a point, if the slope stays the same everywhere for a linear function, then no matter where we are on that function, then the derivative of a linear function or the instantaneous rate of change is just going to be the slope of that function. Does that fully answer your question? All right, great. Then who else has a topic that they'd like to discuss a little bit? Charisma?
Growth or decay?
Growth and decay. So do you mean in terms of exponential functions? Okay. So let me go back to the chapter 1 notes here. So we're going to go to section 1.4. I think that was the section on exponentials. Or was it 1.5? I think it's 1.5. Yeah, here we go. Section 1.5. Okay. So we want to discuss, I guess just generally, exponential growth and exponential decay. Okay? So this was when we had these equations, okay? And we call an equation an exponential equation when the independent variable appears in the exponent. Okay, so let me just remind us that a function like f of x equals x squared, even though there is an exponent, we would not call this exponential. We would say this is not an exponential function. For brownie points, can anybody tell me what kind of function x squared is? Quadratic. Any other terms we could use to describe the function x squared? Sorry? It is a polynomial. It's a monomial, yeah, I guess, technically, because one term. But monomials are also polynomials. And how about power function? Is it a power function? Yeah, it is a power function. The k here, okay, if the power function has the form kx to the p, right, the k is 1 and the p is 2. So it's also a power function. Okay, but this is not an exponential function. What is an exponential function is something like f of x equals 2 to the x. Okay, do you see the difference between those two? We have the variable in the exponent. Okay, so how do we determine whether a function has exponential growth or exponential decay? Okay, well there's two basic forms for exponential functions. The first form is p naught times a to the t, or p naught times a to the x, whatever variable you're using, okay? So the p naught is your original amount of some substance, so it's just a number. And the a is also just a number, okay? Just a number. And the t here is our variable, right? So what we said was, well, this process, as t goes up, okay, here's how the table kind of looks, okay, as t goes up. So as t goes from 0 to 1 to 2 to 3, let's take a look at what happens to p of t. Well, p of t starts as p naught times a to the 0, which is just p naught times 1, which is just p naught, right? And then if t is 1, then we've got p naught a to the 1 equals, well, this is just p naught times a, right? But if t goes up to 2, p naught a to the 2, that's like doing p naught times a, okay? And p naught times a to the cube is just p naught times a times a times a. Okay, so what we see here is as the t value goes up, what's happening from one step to the next is we are multiplying by a each time. Okay, so we take a number, and as t goes up, we multiply by a each time that t goes up by 1. Okay, so this can help us to see why this number is going to grow if a is bigger than 1. Why is it going to grow if a is bigger than 1? Well, if I take a number, okay, if I take a number like whatever this number is, and I multiply it by a, well, the way I decide whether that number got bigger or smaller depends on if a, the number I multiplied by, is bigger or smaller than 1, right? if I take a number and I multiply it by 1/2, the number gets smaller, right? But if I take a number and I multiply it by 2, then the number gets bigger. Okay, so this is how we determine whether we have exponential growth or exponential decay. It depends on what is the number which is attached to the exponent. Okay, so if that number is bigger than 1, we have growth. If it's smaller than 1, we have decay. Does that clear things up? Okay, so this is how it looks for if we have an exponential function in, I guess, what we call kind of just standard form, or this is what it would look like if we were doing annual interest, right? But there's another kind of exponential decay and exponential growth, which is called continuous exponential growth or continuous exponential decay. So let me really quickly go back to that section, which I think was maybe I don't even know what it was. Let me see if I can find it. I think it's 1.7. Or was it right here? Okay, here we go. So it was about converting between exponential forms. Okay, so we said that the two common exponential forms are this one where we have p naught a to the t and p naught e to the kt, right? And this is the one which we use for what we call continuous. So this one is what we use for the continuous exponential growth. Or why don't we just call it a continuous exponential function? Okay? All right. So whenever you see the word continuous, you better be thinking about p naught e to the kt. Okay, so how do we tell if p naught e to the kt represents growth or decay? Well, what we really want to understand is, I know that if I convert it back to the annual form, okay, I know that a is just equal to e to the k, right? And I know that if a is bigger than 1, then I get growth. So I know a is bigger than 1 tells me I get growth. And I know that if a is bigger than 1, then, well, a is just simply equal to e to the k. So if I want to know what should k be in order for me to get growth, well, I just need to solve the equation that e to the k is bigger than 1. Because e to the k is the same thing as a. So if a is bigger than 1, we have growth. If e to the k is bigger than 1, we have growth. So the way we just figure out what happens here is we just take the natural log on both sides. And we get just k on the left-hand side, right? ln of e to something is just that thing. And then what's the right-hand side? What's ln of 1? What's ln of 1? Not 1, but 0. I saw somebody put it up. I think that was Kevin. No, not Kevin. What's your name again? Jake. Jake, right? Yeah, okay. That was Jake. You guys are both tall. Okay, so this means that k should be larger than 0. Okay, so that's how we tell whether an exponential function, which is a continuous exponential function, is going to be having growth or decay. All right. I think that's all I want to say about that. Charisma, do you have any lingering questions on that? Okay, does that clear things up? Sweet. All right. Then let's move on to a new topic. So any other students have something they want to talk about? Hannah?
Can you talk about doubling life and half-life, with it in
Absolutely.
doing the exponential functions within them, how problem
Yes, I can. I think that might even be in the same section, or maybe the next section. Half-life and doubling time. Here it is. Okay. So half-life and doubling time, okay, we should remember that half-life and doubling time is a concept which really only applies to exponential functions. Okay, I mean not only, but this is the context where we care about half-life and doubling time problems. Okay, because half-life problems discuss radioactive isotopes which decay exponentially, and doubling time typically refers to money, right? Which is, in today's day and age, we use compound interest, which is an exponential form. Okay, so half-life and doubling time, we're always talking about exponential functions. So if we see something like that, we should immediately be thinking about p naught e to the kt or p naught a to the t. Okay, so what is the half-life and doubling time? Well, the half-life, okay, if we have something which is decaying, okay, which means that the a value is what? What should the a value be like if our function is decaying? Less than 1, right? So if our a value is less than 1, or if our k value is less than 0, right? Then we're going to be talking about half-life, okay? Because our function is decaying in time, right? So we talk about the amount of time for it to have half left. There's no amount of time for which it would be double what it was before, because it's not growing, it's decaying. Okay, so doubling time we use for the other scenario, right? And what is it? Well, it's defined to be, okay, it's defined to be the time t that it takes, such that if I plug t into the function, I have exactly half left from what I started with. Okay, I have exactly half left from what I started with. Okay, so the way we do that, is, let me move this up here and add a page, is the following. So if we know p naught and a, so say we have p of t equals p naught a to the t, we want to find, so this is for half-life. So we know that a is less than 1, for example. So this is a half-life problem. Well, what do we want to do? We want to find the t value such that p of t is equal to 1/2 of what we started with. And the way I'm going to write that is just 1/2 times p naught. Okay, in fact, I don't even need to know what p naught is. I just need to know that a is a number less than 1. And here's why. I know that p of t is just p naught a to the t, right? And I know that after a certain amount of time, I have half of p naught left. Okay, so whatever was the starting amount, I have half of it left. And this is going to be equal to what I get if I plug t into the function, which is, of course, p naught a to the t. Okay? So 1/2 p naught is equal to p naught times a to the t. So how can I proceed from here if I want to know what t is? Yeah, I can use logs. Do I want to use a log right away? Can someone explain why I shouldn't use a log right away? Yeah, the trick here is if I take a log on the right-hand side, which I'm guessing what your goal is with the log is to get the t down in front, right? But if I take a log on the right-hand side right away, then I have log of p naught a to the t. And I can't bring down the t because although the t is a power on the a, the t is not a power on the p naught, okay? So I can't just bring down the t right away. I have to do something first, which I think what we should do here is first just divide both sides by p naught. And that just cancels out p naught. So this is why we don't need to know what the starting value is, okay? And we just reduce to the equation 1/2 equals a to the t. Right? Which makes sense, right? What we want to do is find the t value such that a to the t is 1/2, because then when I do plug in t, I'll get p naught times 1/2, right? That's what I want to have, half of what I started with. Okay, so now I got 1/2 equals a to the t, and now I think I can go ahead and apply logs. So I get ln of 1/2 equals ln of a to the t, and now we can use our super special rule about logs, which says that ln of something to a power is the same thing as that power times ln of the base. And now what can I do? Yeah, this equation has the form number equals a variable times a number, okay? If I asked you to solve the equation 3 equals 2x, what would you do? You would just divide both sides by 2 to get x by itself, because it's just being multiplied by a number, so we divide by that same number. Well, ln of a is just a number, so all I'm going to do is this exact same process. I'm just going to divide both sides by ln of a. So I get t is equal to ln of 1/2 over ln of a. Okay, and if you want to know, yes, you can use this formula to just get the half-life right away. But if you're going to use it on the exam, I want you to write down that this is the formula which you can use to find the half-life, okay? I don't want to see you just write down what the number is with no work, okay? So you have to write down this formula and tell me, okay, I remember from class that this is the formula which you can use to find the half-life of a substance. Which will only work, by the way, if your function is in this sort of annual decay form, which most of the time radioactive isotopes are given in the continuous decay form. So let me show you how that works really quick. We would have P of t equals P naught e to the kt, and now what we want is for this number, e to the kt, to be a half, because then we would get half of what we had before. So 1/2 P naught equals P naught e to the kt. This tells me that e to the kt equals 1/2. And now I take logs. ln of e to the kt equals ln of 1/2. And therefore I get kt just on the left-hand side, because ln of e to something is just that something. And that's equal to ln of 1/2. And therefore t is equal to ln of 1/2 divided by k. Okay, which makes complete sense because ln of a is equal to k, if you remember that relationship. Okay, so that's how you do it with the continuous model. Okay, so what would I do if I wanted to do a doubling time problem? If I wanted to do P of t equals P naught a to the t, and a is bigger than 1, and I'm doing a doubling time, what do I do in this circumstance? Yeah, I'm just going to set P naught a to the t equal to 2 times P naught. I want to know the amount of time t that it takes such that when I plug it into this formula, I get twice what I started with. So if I started with P naught, then twice that would just be 2 times P naught. Okay, so I'd solve this equation in the exact same fashion. All right, I forget who was asking about half-life and doubling time. Hannah, you feel a little bit better about it now? Okay, should we do a quick example? That one's too long. Here we go. All right, so the half-life of an experimental drug is 7 hours. Okay, well, this isn't really a doubling time problem, is it? Okay, I guess we do have to use. What is the doubling time of infected people? Okay, so here we go. So we got a virus discovered in the biology department at our university. So Scott spilled hot coffee on his professor, who threw the vial with the virus, shattering it on the floor. A group of 15 people in the lab got infected and quickly changed. Okay, so 7 days later, there were 94 people infected. Okay, so we're supposed to find an equation, P of t, for the number of people infected t days after the outbreak began. Okay, so I can do this using either p naught a to the t or p naught e to the kt, all right? Doesn't matter. But I don't see anything in here which says that it's spreading continuously or that we should use a continuous model, so I'm just going to use p naught a to the t. So I think that one's a little bit easier. So I'm going to do p of t equals p naught a to the t. And my goal is to find p naught and a. Well, how about p naught? Can we immediately identify what p naught is? Yeah, 15, right? It's the original amount, okay? Which in this case, the original amount of people who got infected was the first people who were exposed, so 15. I think that's a great start. And how can I find a?
Divide the number of people who got infected after 7 days by those that initially got infected.
Yeah, it's definitely going to have something to do with how many people were infected 7 days later. How can I incorporate this into an equation? I want to take this information and write down an equation. Gino, did you have an answer?
I don't know how you put in an equation, but I know that t would be 7, we have to equal 8 to the t power to equal 94.
Yeah, okay, I think you got it exactly right. The time is 7 days, so that's the t value. So we get 15 times a to the 7, and this number tells us how many people were infected after 7 days, which is 94 people. So this is equal to 94. And now can I figure out what a is? How do I do it from here? Yeah, just divide both sides by 15, so I got a to the 7 equals, okay, let's bust the calculator out. 94 divided by 15 is 6.27, okay? And now I get a by doing what? Natural log? 7th root. How do I do a 7th root on my calculator? That's right. The 7th root is the same as the 1 over 7th power. That's how I do it on a calculator. Okay, so now I'm just going to take all of this to the 1 over 7th power. Okay, so let's do that. I got 6.27 to the parentheses 1 divided by 7 end parentheses, and I get 1.3-ish. Okay, I'm rounding a little bit for this problem, just to make it simpler. Okay, so we get a equals 1.3. So that's 1.3. So my equation, all told, is 15 times 1.3 to the t, right? Okay, so now let me ask a question. How many percent per day is the virus growing by?
Like
1.3%?
30%.
30%. How do we get 30%?
Well, a equals 1 plus the power. So you just do 1.3 minus 1, you get 0.3, and times 100 equals 30%.
Yeah, Alyssa just absolutely demolished this question. Okay, so the answer is, if A is 1.3, that's the same thing as 1 plus R. Okay, if we subtract 1 on both sides, that tells us that R is equal to 0.3. Which means if we multiply that times 100, we get 30% per day. Okay? So, if you have a bank that's offering 30% interest, okay, then the R is going to be 0.3 and your A is going to be 1.3. Okay, great. So let's do the second part, which is what is the doubling time? Well, I know that P of t equals 15 times 1.3 to the t. And what is my goal here? Is to find t, the amount of time, such that what happens? Yeah, such that the number of people infected has doubled from the starting amount. How can I write that down mathematically? Find t such that what is true? Yeah, find t such that 2 times p naught. How can we finish this, make this a full mathematical statement? Sorry?
You equate that to P of t, right?
Equals p of t, exactly. So we want to find the amount of time t such that if I plug it into the function, it tells me that we have double the amount that we started with. Okay, well I know what p naught is, and I know what p of t is. So I can rewrite this equation as 15 times 1.3 to the t is equal to 2 times p naught is 15, right? So that's 2 times 15, which is 30. So I'm trying to find the t value such that this equation is true. All right, now what do you guys think if I apply logs on both sides? Does that sound like a good idea? Not yet. Why not yet?
It would be attached to the 15 and t doesn't apply.
Exactly, there's no t power on the 15, so I got to take care of that little piece first. So I'm going to divide both sides by 15. So I get 1.3 to the t equals 2, right? And now I can find out what t is pretty easily, right? I just take the natural log on both sides, and I get t times ln of 1.3 equals ln of 2. And ln of 1.3, let me ask you something. Is that a function or a number? It's a number, right? It's what I get if I plug 1.3 into the natural log function. If I plug a number into a function, I get a number, right? So this is just a number, so all I do is just divide both sides. So it's ln of 2 over ln of 1.3, which, let's do it on our calculators. It would be, okay, ln of 2, where's my ln button? Divided by, parentheses, ln of 1.3, end parentheses, and I got 2.64. Okay, 2.64 what? What are my units? Days, right? This is the amount of time t, so this is days. Okay, let's see, does that jive with us? If we're growing at about 30% per day, it says it's going to take a little more than 2 days and a little less than 3 days for the amount of infected people to double. Does that sound about right? Yeah, I think that sounds about right. We should always check and make sure. Go back to the original problem and think about it. Well, if we're growing at 30% per day, then how long do I think it's going to take to double? It'd probably be, somewhere 2 or 3 days, right? Because plus 30%, plus 30%, plus 30%. But you got to remember to apply that 30% to the additional gains that you got in the last 2 steps as well. So I think 3 would definitely take us over a doubling point. All right. So, Hannah, are we happy? All right, cool. Let's move on to another topic. I think Seb's got one.
Well, I had a question.
Oh, okay, sure, yeah.
If we're, like, now that we have our scientific calculators and stuff now, are we going to leave it as equals ln, the 2 over ln?
I'll be specific in the instructions. I'll either say round it to the nearest hundredths place, or I'll say you can leave your answer in a general form, something like that. Any other questions? Or you can also just raise your hand and ask me during the exam. It's also an option. All right. Next topic. Has anybody got one for me?
So can we use like the doubling time kind of thing to figure out if the question is asking how long it would take for the calculation to triple?
Sure. Yeah. So if I understand you correctly, the question is, what if the question asks not what is the doubling time, but what is the time taken for the number of infected people to triple? Is that right? So how would I change my approach here? Yeah, all I would change is I want to find the amount of time t such that the amount of infected people is not 2 times what we started with, but 3 times what we started with. So we'd put a 3 here. Okay? And then there'd be a 3 here. Right? And so on and so forth. So that's the only difference if it was a tripling time, or quadrupling time, or whatever amount of time. All right, any more questions on the exponential problem? On this doubling time stuff? Okay, then let's move on to a new topic. Does anybody else have any other questions from other topics that they want to discuss? Yeah, Brendan?
Can we review about power functions and proportionality versus inverse proportionality?
Okay, sure, yeah. So the question is, can I review power functions and proportionality? Yes, I can. Okay, so let's just briefly recall. What are power functions, what are polynomials, and what are quadratics? Okay, so let's have this is enough space. Okay, so polynomials. Now, let's start with power functions. Okay, p of x is a power function if p of x is equal to k x to the p, where k and p are real numbers and p is not 0. So let's have a bunch of examples of power functions. 2x is a power function. How about 3x to the negative 1/2? Is this a power function? Yes. K is 3 and p is negative 1/2. Okay, how about x root x? This was on the quiz. Is this one a power function? It is a power function. Can anyone argue why? Yeah, the square root of x can be written as a power. It's the power x times x to the what power? 1/2. If I have x times x to the 1/2, how do I simplify? I want to write this as a single power. I have x to the 1 times x to the 1/2. If I multiply numbers like this, what do I do with the powers? I add them. What would be the situation where I multiply them? Yeah, that would be if I had something like x to the 1/2 cubed. If I do something like this, then I multiply the powers. But if I have x to a power times x to some other power, I add those two powers together. Okay, so if I add 1 to 1/2, I just get 3/2, right? And now, do we think that this is a power function? Yeah. What's the k value? 1. What's the p value? 3/2. So are those two numbers real numbers and p isn't 0? Yes, so that's a power function. Okay, one more. X to the, no. Let's do e times x to the pi. Power function? Yes, e is a real number, pi is a real number. And pi is not 0, right? It's 3.14 something. 1415926, maybe. Okay, and e is something like 2.718 or something like that. Okay, so those are all power functions. Now let's move on to quadratics. Quadratics. Q of x is a quadratic function if q of x can be written ax squared plus bx plus c, where a, b, and c are real numbers, and one of them shouldn't be 0. A shouldn't be 0, right? A shouldn't be 0 because otherwise this part would just be 0, and we'd just have bx plus c. What type of function is bx plus c? Linear. Very good. Okay, so let's have some examples. Quiz you again. How about 2x squared minus 3x plus 1? Quadratic? Yes. How about x squared? I'm seeing some no's and some yeses in the crowd. It is a quadratic. Can someone argue why it is a quadratic?
Because b and c are just 0.
Yeah, b and c are allowed to be 0. All we say is that a, b, and c are real numbers. Is 0 a real number? Yes. So b and c can be 0. The only thing I say is shouldn't be 0 is a. So x squared is a quadratic function. Okay, let's do another tricky one. What about this one? X minus 1, quantity squared. Is that quadratic? Yeah. All I have to do to see that this is quadratic is expand it. So someone tell me, is this just the same as just x squared plus 1 squared, which is just x squared plus 1? No, what do I have to do to expand that? FOIL, F-O-I-L, first, outside, inside, last, okay? The way I do this, it's not like this. I can't distribute powers like that. I get x minus 1 times x minus 1, and then I FOIL, okay? FOIL means first. So first I multiply x times x. I get x squared, then I add. And then I multiply x times negative 1, that's the outsides, right? And that's negative x, and then I get a plus, and then I multiply the insides. That's negative 1 times x again. So I get another negative x, and then a plus, and then I do the L, which is the last, which is negative 1 times negative 1, which is 1. So I get x squared minus 2x plus 1. All right? Let me move this somewhere else. Okay. Let's add a page because I'm running out of space. Okay, the last one was polynomials. So p of x is a polynomial function if p of x equals an times x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a1 times x to the 1 plus a0 times x to the 0. Well, a0 times x to the 0, anything to the 0 power is just 1, so that's really just a0, right? Okay, so a polynomial function has this form, where n is an integer, and it's a non-negative integer. N is larger than 0. Okay, so n can be any whole number like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, forever, right? Any of those numbers, okay? And then, actually, all the other powers are also going to be integers, right? Because if I have an n, which is an integer, and I subtract 1 from it, I get another integer, right? 4 minus 1 is 3. 6 minus 1 is 5, right? I subtract 1 or 2 or 3, any natural number from any other natural number, and I get another integer, right? Okay, so let's have examples of these. Examples of these could be like x cubed plus 2x squared plus x. Oh, I forgot to say what an are. An are just real numbers. And I guess at least one of them should be non-zero, so why don't we just call that n? The an's are in R. How should I write that? I don't want to write that like that. I want to write this like AI. AI are in R. And an, which is this specific one, the leading term, is not 0. Okay, there we go. So x squared plus 2x plus x minus 17. Polynomial or not polynomial? Yes, all the numbers an are a3 is 1, a2 is 2, a1 is 1, and a0 is not 17, but negative 17. Okay? All right, that's an example. How about x to the 57? Polynomial or not polynomial? It is a polynomial. Yeah. A57 is 1, and A56 through A0 are all 0. So this is also a polynomial. Also things like x minus 3 times x plus 5 times x minus 71. All of these. Also times x plus pi. How about that? If you FOIL all this crap out, you'll get a polynomial. Okay, I don't want to spend any more time on polynomials because I want to talk really quickly about proportionality before we close, because that's the last question. But really quickly, any questions on power functions, quadratic functions, and polynomial functions? Yep.
So could a power function be a polynomial function?
Yeah, when is a power function going to be a polynomial? Yeah, we need the exponent to be a non-negative integer. Okay, I also forgot to mention k should not be 0 either, obviously. So then it would just be 0. Okay, so it's going to be, a power function is going to be a polynomial if and only if p is a non-negative integer. A number like 1, 2, 3, 4, 5, these numbers. Okay? When is a power function going to be a quadratic? Yeah, if p is 2, then a power function is a quadratic. When is a quadratic going to be a power function? Sorry. Yeah, when it's only the x squared term. So what does that mean for a, b, and c? It means b and c are 0 and a is not 0. If that's true, then a quadratic function will be a power function. Okay, you can see all these different situations. Okay, 3 minutes left. Let me talk about proportionality really quickly. So the two rules we had for proportionality were about direct proportionality and inverse proportionality. Okay, so we say that y is directly proportional to x if y equals k times x. Okay, where k is a number which is not 0. Okay, so y equals k times x, so it's a linear function, right? If y and x are proportional. But if we were to say y is proportional to the square of x, what would that look like? Y equals what? K times x squared, okay? All right, and inversely proportional just means that we, instead of multiplying k times x, we divide k by x, okay? So it's about taking a number k and doing something to it. You're either multiplying by something with the variable if it's directly proportional, or you're dividing by something with the variable if you have inversely proportional. Okay, so let's see a quick example of that. All right, so my weight on the moon, or your weight on the moon, is proportional to your weight on Earth. Okay, so let's call our weight on the moon, why don't we call that m? And we'll call our weight on Earth, we'll call that e. So what's my equation going to look like? If the weight on the moon is proportional to the weight on Earth, I'm going to have something equals k times something, right? Which one goes on which side?
M go on the left side?
Sorry?
Would the M go on the left side?
Yeah, the m goes on the left side, and the e goes on the right-hand side. Great. So the question is, if Jacob weighs 38 pounds on the moon, how much does he weigh on Earth? Well, I can just plug in 38 pounds for m, right? Only there's one problem. If I do that, I get 38 equals k times e. And we want to know what e is. So what's the problem? I don't know what k is, right? So I can figure out k using the other part of the problem. It says the constant of proportionality is 0.1655. Okay, we didn't even have to calculate it. So 38 is just going to be equal to 0.1655 times e. So if we want to know e, all we have to do is divide 38 by 0.1655 to get e. Which if we do that, we got 230.3 pounds, right? Okay, so that's a simple example. Gino? Yeah?
You said something about being able to calculate k. How do you do that?
Yeah, so one thing they might say in this situation is they might say Mary, some other person, weighs 115 pounds on Earth and I don't know how many pounds, how about like 17 pounds on the moon. And then you'd use this to say, okay, well then 17 is equal to k times 115. And you figured out k using that other information. Yeah, so that would be a situation where we're not told what k is.
Yeah, that was like a little more complicated. Sorry.
Yeah, no worries. All right, well that's it for today. Thanks for your attention. Office hours are going to start at hopefully about 4:30 today on Microsoft Teams. So hope to see you there.